Beneath the phosphates of Morocco lies the record of a vanished sea, crowded with hunters, drift feeders, and animals built for a world close to collapse. OULED ABDOUN is not just a fossil site, it is an ecosystem caught in the final moments of the Cretaceous. Near present-day Khouribga, in central Morocco, the ground opens onto a lost sea. The OULED ABDOUN Basin, known for its phosphate deposits since 1908 and mined on an industrial scale since the 1920 years, preserves an exceptional record of the very end of the Cretaceous. Back then, this part of Africa stood on the margin of a warm, shallow epicontinental sea at low latitude. Sunlit waters spread across the basin, while wind-driven upwelling brought nutrients from depth and fueled a dense marine food web. Phosphate-rich sediments built up in that productive seaway and locked away the remains of the animals living within it. This video is about that ecosystem, not a single species, but an entire marine world, recovered from the rocks of OULED ABDOUN at the edge of the Cretaceous, Paleogene boundary. Among the more unusual animals of this assemblage is Baculites, an ammonite whose shell abandons the familiar spiral and grows into a long, straight tube. That shell still began as a minute coil, then expanded into a chambered structure linked by a siphuncle, allowing buoyancy control through the water column. Its form suggests stability rather than pursuit, and isotopic work places it away from both seabed and surface, in the middle layers of the sea. Exceptionally preserved remains indicate a diet of small pelagic organisms, which gives Baculites a precise ecological role, not a dominant hunter, but a persistent midwater feeder, one of the many bodies carried through this marine system by currents, density, and light. Schizorhiza gives this fauna a sharper geometry. It was a ray, but one equipped with a long, reinforced rostrum edged by dense batteries of denticles, arranged so tightly that each side functioned as a continuous blade. Growth at the tip and nested replacement within the roots kept that cutting margin active through life, turning the snout into a specialized instrument rather than a simple ornament. Its anatomy points to an animal that could sweep, strike, and slice through schools of smaller prey with controlled lateral movements. In this ecosystem, Schizorhiza reads as precision-made biological, a cartilaginous hunter built around one highly refined weapon. Cretalamna introduces a more familiar predatory design, though one built with notable efficiency. It was a medium-sized lamniform shark, roughly comparable in length to a modern porbeagle, carrying broad triangular teeth flanked by smaller lateral cusplets, all edged for cutting. The arrangement of those teeth suggests a hunter meant to seize, pierce, and slice rather than crush. Its jaws and dentition are close enough in form to living lamna that small to medium-sized bony fishes remain the most plausible prey. Within this marine system, Cretalamna reads as a fast, adaptable pelagic predator, less specialized than some of its contemporaries, but well placed to exploit whatever movement the water delivered. Squalicorax shifts the tone again. This was a compact, fast-swimming shark, commonly around 2 to 3 meters long, armed with rows of small, curved, serrated teeth. Those teeth worked less like spikes than like blades. Skeletal evidence suggests a feeding style comparable to that of the modern tiger shark, with flesh cut by repeated sawing motions rather than simple puncture. Broken and chipped teeth show that feeding could be violent enough to damage the dentition itself, while rapid replacement kept the cutting edge functional. Within this fauna, it reads as an efficient meat processor, and the fossil record repeatedly places it at carcasses as one of the major scavengers of its seas. Pycnodonts added a different kind of fish to this ecosystem, deep-bodied ray fin specialists with powerful crushing teeth, adapted to break hard-shelled prey rather than pursue fast-moving animals in open water. Stratodus gives the bony fish fauna a far harsher profile. In the Moroccan phosphates, it is recognized as a large open-sea predatory actinopterygian, and a nearly complete skeleton from North America shows an elongated body with a long dorsal fin, paired fins, and rows of osteoderms along the body. Its jaws were armed with dense batteries of small teeth. From the first description onward, the palate and premaxilla were already noted for carrying crowded tooth fields rather than a few oversized fangs. Taken together, those features suggest a hunter built to seize and hold struggling prey in motion, adding yet another predatory design to this marine system. Enchodus was a teleost, but one built with a predator's proportions, a large head, a single oversized fawn on the palatine, and a matching dentary weapon set near the front of the lower jaw. Together, those elements turn the mouth into a gripping apparatus, suited to seizing slippery prey in a brief, decisive strike. Faunal studies consistently interpret Enchodus as an active hunter with piercing dentition, most likely feeding on other fishes. Yet the same record places it below the largest carnivores around it. It hunted efficiently, and was hunted in turn, occupying the unstable middle ground of a crowded marine food web. Alienochelys takes the turtle lineage in a markedly different direction. It was a large marine form with an unusually broad, compact skull and a feeding apparatus specialized for powerful crushing, a combination described as distinct among known sea turtles from these phosphates. The jaws suggest force concentrated across expanded biting surfaces rather than speed or slicing efficiency, which points to a durophagous role within the ecosystem, probably focused on resistant prey. In practical terms, Alienochelys occupied a mechanical niche that contrasts sharply with the sharks and predatory fishes around it, less a pursuer than a processor, built to break what other animals could only bite. Ocepechelon may be the most structurally unusual turtle in this assemblage. Its skull was enormous, yet the jaws ended in a long bony tube with a small, forward-facing mouth, a design that converges more with pipefishes and beaked whales than with any familiar sea turtle. That architecture points to suction feeding, a rapid expansion of the buccopharyngeal cavity drawing prey inward through a tight circular opening. The elevated eyes and nostrils further suggest an animal moving near the surface, scanning the water while bringing in prey whole rather than processing it by force. Ecologically, Ocepechelon occupied a distinct channel in the food web, built around pressure, precision, and a feeding method unique among known turtles. Palaeophis belonged to a lineage of aquatic snakes known mostly from vertebrae and ribs, yet those fragments are enough to reveal a body already committed to life in the water. In the large African forms, the trunk was elongated, the vertebrae mechanically adapted to aquatic motion, and their internal vascularization suggests growth and metabolic intensity above that of the biggest living snakes. The result is a striking animal in functional terms, a marine serpent, heavy-bodied and specialized, moving through coastal waters as one more large predator in a system already crowded with them. Beyond the sharks and bony fishes, this sea also supported one of its most formidable radiations, a remarkably diverse assemblage of Mosasaurs, filling multiple predatory roles at once. Eremiasaurus belongs to the same radiation, but its anatomy is more intricate than its size first suggests. It was a mid-sized mosasaur, around 5 meters long, with a sturdy skull and one of the most strongly heterodont dentitions known among these reptiles. At the front of the jaws, the teeth were straight and conical. Farther back, they became laterally compressed and blade-like, before shifting again toward broader posterior crowns. That sequence suggests a predator able to grip, slice, and control prey through different parts of the bite. Its tail anatomy also points to an efficient swimmer, giving Eremiasaurus the profile of a fast, versatile hunter within an already crowded mosasaur assemblage. Carinodens occupied the opposite end of the mosasaur spectrum. It was a small, unusually specialized form, with long, slender jaws and a dentition unlike the cutting batteries of the larger predators around it. At the front of the mouth, the teeth were narrower and more pointed, suited to seizing and positioning prey. Farther back, the crowns became lower, compressed, and mechanically adapted for crushing. Microwear studies support that interpretation, indicating repeated contact with hard food items, most plausibly shelled benthic invertebrates. Carinodens therefore adds a quieter specialization to this assemblage, a compact shellbreaker working through the lower levels of the food web. Prognathodon carries mass where other mosasaurs carry edge. The skull was broad, the jaws massively reinforced, and the teeth thick, conical, and built to transmit force deep into prey rather than simply slice flesh. Recent work on the Moroccan phosphates places this dental architecture in a guild adapted for smashing large, resistant animals, including heavily built vertebrates such as turtles. So within the same sea that supported swift pursuit hunters and compact shell crushers, Prognathodon occupied a heavier register of predation, a marine reptile defined by bite strength, mechanical control, and the ability to break through armor as well as soft tissue. Stelladens enters this fauna almost as an anomaly. Known from a fragment of the lower jaw and a few associated teeth, it appears to have been a mid-sized mosasaur, yet its dentition is unlike that of any better-known form in the basin. The crowns were short, triangular, and recurved, but the inner face carried large serrated ridges separated by deep grooves, creating a cutting surface with a geometry unique among described mosasaurs. That kind of tooth does not suggest simple puncture or ordinary slicing. It points instead to a highly specialized feeding method, one still difficult to define from the available material. In a fauna already rich in experimentation, Stelladens stands out as one of its most cryptic designs. If Xenodens is accepted as a distinct mosasaur, then it represents one of the strangest feeding designs in the entire assemblage. It was a small animal, yet its jaws carried short, flattened teeth packed edge to edge into a continuous serrated margin, more reminiscent of certain cutting sharks than of other marine reptiles. Recent CT work suggests that even the implantation and replacement of those teeth were unusually specialized. Functionally, this points to a bite designed less for crushing than for rapid slicing, perhaps on fish, cephalopods, crustaceans, or torn flesh. In a fauna crowded with predatory experiments, Xenodens remains one of the most peculiar. After the smaller Durophagous forms, Globidens expands the same mechanical idea into a much heavier predator. Its skull was stout, its jaws tightly built, and the teeth changed along the row, culminating in swollen, almost spherical posterior crowns whose ridged enamel and rounded geometry were suited to transmitting force into resistant prey. Moroccan material shows that this was a highly specialized dentition rather than a variation on the cutting teeth seen in most mosasaurs. The function becomes even clearer from direct evidence. One specimen preserved bivalve shell fragments in the stomach region, including inoceramids that had been crushed before swallowing. In ecological terms, Globidens was one of the clearest shell breakers in the entire assemblage, a reptile engineered to turn armor itself into food. With Pleurodens, the image of a mosasaur shifts away from broad cutting jaws and toward sensory search. The skull was long, flat snout, and lined with an unusually high number of small, hooked teeth. In the Moroccan species, the orbits are reduced, while the snout carries numerous neurovascular openings. That combination suggests a predator less dependent on vision, and more attuned to touch and chemical cues, perhaps in the manner of modern marine snakes. Despite that delicate-looking dentition, it was a large animal, with skulls indicating bodies around 5 to 6 meters long, and some referred remains hinting at even greater size. Pleurodens seems to have hunted smaller prey, but by following a very different sensory route through the same sea. Seen from the skull forward, Congeria appears built around force. The snout was short and heavily reinforced, the jaws deep, and the front teeth enlarged into compressed, dagger-like blades that interlocked when the mouth closed. That architecture increased mechanical advantage and favored a bite capable of opening large prey with deep cuts rather than simply puncturing it. At roughly 8 meters in length, it ranked among the larger hunters of this ecosystem, but with a predatory design clearly separate from the broader-jawed giants around it. Small orbits and a simple pattern of snout foramina further suggest a hunter that may have relied less on visual pursuit than on ambush and other sensory cues, perhaps targeting sizable fish and other marine vertebrates in turbid or dim water. Historically, some of this Moroccan material was referred to Platycarpus, although that attribution is now unstable, and the best-known remains have been reassigned by several recent studies to Gaviolimus instead. Used here in that older sense, Platycarpus evokes a more lightly built plioplate carpine, a streamlined mosasaur shaped for efficient open-water movement rather than brute force feeding. Exceptionally preserved specimens from outside Morocco have shown that true Platycarpus carried a deep tail fluke and a hydrodynamic body, giving it the profile of a fast pelagic swimmer driven mainly from the tail. So even if the name itself may no longer be the correct one for this basin, it still captures an important ecological image within the fauna, a narrower-jawed pursuit hunter moving through the water with speed, control, and far less emphasis on crushing power than the heavier mosasaurs around it. Gaviolimus carried one of the most unusual head shapes in this entire assemblage. The snout was long and narrow, the teeth high, sharp, and closely interlocking, and the nostrils had shifted far back along the skull, producing a profile that recalls a gharial more than a typical mosasaur. At roughly 6 meters in length, it was a substantial animal, yet its design points away from bone-crushing power and toward precision. The jaws seem suited to rapid lateral snaps through dense schools of prey, while the tooth form suggests a diet dominated by small fish and soft cephalopods. In ecological terms, it occupied a cleaner, narrower predatory channel than the heavier mosasaurs around it, less a breaker of armor than a specialist of fast, narrow-bodied prey moving through the open water. Among the mosasaurs here, Halosaurus was a lighter design. Adults reached roughly 3 to 4 meters in length, and the known material shows a long, narrow jaw carrying a crowded row of delicate, recurved teeth, each with fine carinae and a subtly ridged enamel surface. Those teeth were poorly suited to crushing armor or dismembering large vertebrates. Their function was more precise, to seize soft-bodied prey and hold it cleanly during capture. Recent ecological work places Halosaurus in the Puresight guild, alongside forms specialized for fish and cephalopods. So within this already varied reptile fauna, Halosaurus reads as a compact mid-level hunter, relying on accuracy, rapid snapping bites, and a feeding style built around smaller, more mobile prey. For a long time, this animal was known mainly from isolated teeth. More complete skulls and mandibles later revealed its real proportions, and the result is telling. This was one of the major large predators of the basin, reaching roughly 8 to 10 meters in total length. The skull was long, relatively narrow, and carried straight, elongate jaws, so its head reads less like a crushing device than like an extended cutting platform. The teeth sharpen that picture further. Their crowns were robust but laterally compressed, edged by fine serrated carinae, faceted along the surfaces, and built in the classic Mosasaurus pattern with a U-shaped cross-section. Functional studies placed this species in the cutting guild, yet the near absence of heavy wear and breakage suggests a hunter that relied less on raw bite force than on placement and efficiency. It probably seized prey first, then opened flesh with controlled cuts and swallowed either smaller animals whole or larger prey in manageable pieces. Large fish, cephalopods, and smaller marine reptiles fit that feeding model well. So although Mosasaurus bogai stood among the apex predators of this sea, it did so by a distinct method, not as a shell breaker, and not as a blunt force giant, but as a long-skulled, high-level predator built for slicing through living tissue with speed and precision. Phalacodon pushes this mosasaur radiation to its most extreme predatory form. At roughly 9 to 10 meters in length, with a broad skull, a shortened reinforced snout, and teeth shaped as large robust cones, it was built to withstand violent contact with substantial prey. Those crowns were thickly enameled, heavily worn, and often broken, which gives a clearer picture of function than size alone. This was a bite designed to seize, tear, and absorb stress rather than simply slice soft tissue. Recent ecological work places it in a distinct crush-cut guild, intermediate between ordinary cutting dentitions and true shell crushers. That matters, because fossils from the same beds include remains marked by digestive acids, suggesting predation on other mosasaurs, plesiosaurs, turtles, and large fish. In practical terms, Phalacodon stands as the clearest apex predator in this sea, an animal whose anatomy implies repeated encounters with prey large enough to resist, injure, and still be overpowered. Historically, some of the plesiosaur remains from these phosphates were assigned to Plesiosaurus, under the name Plesiosaurus mauritanicus. That label now survives mainly as a historical reference, because the original material is too fragmentary to define a clear genus with confidence, and later work recognizes Xerophosaura as the valid named plesiosaur here. Used in that older sense, Plesiosaurus still evokes a very different predatory design from the mosasaurs, an elasmosaur great hunter, long-necked, narrow-jawed, and equipped with slender teeth suited to seizing smaller prey in quick, controlled strikes. In the structure of this ecosystem, it adds reach rather than force, precision rather than impact. Xerophosaura restores a very different body plan to this ecosystem. It was an elasmosaurid, part of a plesiosaur lineage that remained rare in these phosphates, and its skull shows a distinctive combination of a short preorbital region, a long straight dentary, and slender recurved teeth ornamented with fine enamel ridges. Those crowns belong to the classic piercing type, suited to gripping small, soft-bodied prey rather than breaking armor or opening large carcasses. So while the mosasaurs divided the sea through cutting, crushing, and brute force, Xerophosaura occupied a narrower predatory lane, a long-necked hunter built around reach, timing, and precise capture. For a moment, the record shifts from sea to shore. Schizorhiza is one of the very few dinosaurs known from these phosphates, and a single lower jaw already gives it a strong profile, deep, bowed, powerfully built, with a broad U-shaped snout and tall serrated teeth set for cutting flesh. Size estimates place it around 7 to 8 meters long, making it a large abelisaurid and one of the last known African dinosaurs of its kind. The structure of the dentary suggests a predator with a short, forceful skull, closer in style to the heavy-headed abelisaurids of southern Gondwana than to the older long-snout hunters once common farther north. Within the wider landscape surrounding this basin, Schizorhiza stands as the terrestrial apex carnivore at the edge of a sea already filled with predators. Toledo adds a quieter kind of dinosaur to this world. It was a small lambeosaurine duckbill, known from two associated upper jaws, and those jaws are already enough to show a distinct feeding design. The tooth row is straight, the crowns are unusually large and obliquely set, and the reduced tooth count suggests a mouth built for processing plants in a different way from the other Moroccan hadrosaurs. The broader pattern is just as interesting. By the very end of the Cretaceous, these duckbills seem to have diversified rapidly into several local forms, each with its own jaw mechanics. Toledo reads as one more branch of that brief African experiment. Agnabia matters less for size than for what its presence implies. It was a small lambeosaurine hadrosaur, known mainly from the upper jaw and part of the lower jaw, with a maxilla carrying 23 tooth positions and proportions consistent with a compact duckbill only a few meters long. Its closest affinities lie with European lambeosaurines, which makes the animal biogeographically striking. In these latest African faunas, a lineage of hadrosaurs had somehow arrived, established itself, and begun to diversify. So Agnabia is more than an isolated herbivore. It is evidence that even near the end of the Cretaceous, dispersal was still reshaping dinosaur communities. Menkeria gives the terrestrial fauna a more delicate herbivore, but not an insignificant one. Known from part of the skull, it was a small lambeosaurine, around 3.5 meters long, and the fused brain case shows that this size belonged to a mature animal rather than a juvenile stage. Its jaws differ subtly from those of Agnabia, especially in the shape of the tooth row, which points to a distinct feeding mechanics within the same broader duckbill lineage. That matters because it suggests real diversification. These hadrosaurs were not passing visitors, but a small radiation already partitioning the plant resources of their environment. Above the water, Atuchin represented a lighter but still highly specialized branch of the fauna. It was a small nyctosaurid, roughly in the range of a large seabird in wingspan, yet its proportions were unusual. The distal wing elements were abbreviated, the forelimb bones were robust, and the overall design points to a flight style different from the long-winged soarers often imagined for pterosaurs. The original description interprets those shortened wings as evidence for fast flapping flight with higher wing loading, while also raising another possibility, that reduced wingspan may have helped during plunge diving or underwater pursuit. The jaws fit that picture of surface or near-surface feeding. The dentaries were fused into a long, narrow, toothless Y-shaped beak with sharp cutting margins, forming a precise instrument rather than a crushing one. Even the holotype shows a fused scapulocoracoid, which means this body plan belongs to a mature animal. Atuchin therefore adds an aerial predator to the ecosystem, compact, efficient, and sharply distinct from the giant pterosaurs sharing the same coast. Khouribga occupied a higher tier in the pterosaur fauna. It was a large nyctosaurid, known from a distinctive humerus about 165 mm long, with a robust shaft, a broad fan-shaped deltopectoral crest, and an enlarged supracondylar process. Those proportions set it apart from Atuchin rather than simply scaling that smaller form upward. adult Atuchin humeri reach only about 102 mm, while Submergia would have carried over 5 times the mass under isometric scaling, and the sample contains no intermediate-sized adult bones. The implication is a separate flight regime, and therefore a separate ecological role, a heavier, more powerful aerial predator moving above the same coastal waters. Tetradraco adds a larger aerial silhouette, but also a note of taxonomic uncertainty. It was first described from a humerus and associated limb bones as a pteranodonid with an estimated wingspan of about 5 meters, its wing marked by a proximally placed deltopectoral crest, a strongly expanded triangular distal humerus, and a short, broad ulna. Later work on an articulated wing from the same phosphates argued that those proportions fit an Asdarchid more closely. Whatever its exact family position, the functional picture remains clear enough. This was a substantial flyer, built around a powerful forelimb and a flight apparatus distinct from the smaller Nyctosaurids sharing the coast, adding yet another predatory layer above the basin's surface. Barbaridactylus suggests that even within the Nyctosaurids, the airspace above this basin was sharply partitioned. It was one of the larger members of that group, with a wingspan of about 4 meters, yet its skeleton was built along a different line from the more compact forms already mentioned. The humerus was long and slender, the deltopectoral crest relatively short and set far down the shaft, and the ulna remained comparatively gracile, all of which point to a flight apparatus tuned more toward sustained aerial movement than rapid, forceful flapping. The fused scapulocoracoid shows that this was an adult body plan, not an immature stage of a smaller species. Its jaws curved upward in a typical nyctosaurid fashion, forming a narrow toothless beak suited to seizing small prey at the water's surface. So Barbaridactylus adds another layer to this fauna, a larger coastal flyer, anatomically distinct, sharing the same shoreline while exploiting it in a different way. Whether the giant Asdarchid from these phosphates truly belongs to Arambourgiania or to a very close relative, the effect is the same. The coastline was overshadowed by one of the largest flying animals known. The Moroccan material is still treated cautiously, and recent work notes that the giant seedy Chenane Asdarchid could represent Arambourgiania or another giant species. But the anatomical signal is clear enough. In Asdarchids, the neck was built from hyperelongate, cylindrical vertebrae, producing a long, stiff reach, while the jaws formed an extended toothless beak suited to precise seizure rather than crushing. That combination gives this animal a striking ecological presence. It was not part of the marine crowd below, but a giant aerial predator moving above it, surveying the margins of the basin and bringing yet another scale of predation into the same landscape. Known from a short chain of associated cervical vertebrae, Phosphatodraco is unusually informative for an Asdarchid. Those bones show a neck that was extremely elongated, lightly built, and mechanically stiff, one of the clearer examples of the Asdarchid design in the Moroccan phosphates. Depending on how the vertebrae are interpreted, the animal probably carried a wingspan of roughly 4 to 5 meters, placing it below the giant forms but well above the smallest coastal flyers. Its importance is therefore functional as much as taxonomic. Asdarchids combined long, shallow toothless jaws with a rigid reaching neck, a structure better suited to precise seizure than to trawling or crushing. In this ecosystem, this pterosaur reads as a measured opportunist, an aerial hunter working the margins of sea and land, taking small prey with accuracy rather than force. Then the system ended abruptly. Around 66 million years ago, an asteroid more than 10 kilometers wide struck the region of present-day Yucatan and opened the Chicxulub crater, triggering the Cretaceous, Paleogene mass extinction. Dust, aerosols, and soot spread through the atmosphere, sunlight collapsed, temperatures fell, and the food webs that sustained seas like this one began to fail from the base upward. Ammonites disappeared. Pterosaurs vanished. Mosasaurs and Plesiosaurs were lost with them, while on land the non-avian dinosaurs also came to an end. OULED ABDOUN preserves that world in extraordinary detail, and for that reason it also makes its destruction feel precise, sudden, and real.